for applications of geomechanics. Like Mr. Nikhil has made the introduction, it is with Petroleum Engineering Association. So we will go on through a lot of slides regarding the application of geomechanics. We will not go through application and software details, but we can provide a lot of information that you can use it. And if you want a lot of details, we can provide separated the course for each topics. Okay. So, welcome to this topics. I think that Nikhil has made the presentation of myself. So, I'm Yusuf, a geoscientist with 10 years of hands-on experience within the conventional and unconventional reservoirs, from sonatic exploration, sonatic and conventional, and also Pertamina Repsol sonatic GV. I have also published 2 papers on one Petro and Journal of African Earth Science on geomechanics. I have also PhD in geomechanics of unconventional reservoirs, and also I am involved as a researcher in the national research program, which is entitled Monitoring of Unconventional Reservoir Stimulation Operation by Microseismic. Okay, so let's go through our objectives. So after completing this workshop, we'll be able to relate the geomechanical concept to drilling and production applications. You can explain the completion applications of sanding. You can also describe the completion applications of hydraulic fracturing, and also finally you can use various geomechanics elements to create a coupled geomechanical model. So this workshop is divided into following steps: introduction, application completion for sanding, hydraulic fracturing, and also fracturing the horizontal wells. And we will finalize by reservoir geomechanics examples. So let's start. So the first question that non-geomechanics and all oil and gas industry engineers can ask is, what is geomechanics? So the geomechanics is a multi-planary discipline which is based on predicting and managing the subsurface deformations by integrating geology, geophysics, and petrophysics information to characterize the subsurface deformations. The second most important question is why we use this geomechanics, or why use the modeling, geomechanical modeling. We have to know that geomechanics is a key element in conventional and conventional exploration and production. The knowledge of the geomechanics and elastic parameters is very helpful to avoid the problems and incident in the oil field by predicting changes that can occur over the life of the field caused by the change of pore pressure, of reservoir pressure, of well bore pressure, and also the temperature pressure. Here in the right side, we have some example of why we should use geomechanics. We have the well-known incident in the oil and gas industry, which is the Deepwater Horizon. So this is a problem due to geomechanics non-estimation of the pore pressure. As you know, this Deepwater Horizon, in fact, it was a problem of wellbore stability and well integrity due to bad estimation of the pore pressure, or some people said that non-estimation of the pore pressure at all. So the reservoir was an overpressured reservoir, means HPHT reservoirs, and began to deliver a high pressure, and everyone know the rest of this drama. So finally, where and when we have used the geomechanics in the oil field. So just to mention that geomechanics is involved from the exploration to the abandonment phases of the life cycle. So from the start, we use geomechanics in pore pressure prediction in the exploration and appraisal phases. So also we can use the wellbore stability in the appraisal and development phases. It is involved in the development and production phases by estimating the fault and fracture permeability, also in the sand production analysis, compaction, also to analyze and predict the case and shear, and also to characterize the fracturing stimulation. The geomechanics, finally, even in the end of the life cycle, it is involved by estimation the depletion, and also when the depletion occur, we can use geomechanics to manage this depletion over the end of life of the field. So the key roles of geomechanics is to reduce the MPT, so reduce cost and minimize the risk. So based on Dodson paper and based also on this data published, we have that 67% of the MPT are due to wellbore stability issues. We can so estimate that the cause of these wellbore stability problems are around 8 billion USD dollar per year. So we can avoid all these loss by only making a comprehensive mechanical earth model to our field. Here we have a summary for the geomechanical applications. So the geomechanics analysis workflow is based on the input data from log data, core data, well logs, seismic data, geological data, and drilling data, and also we can use the WSM, the Earth stress data published public ones. So this data can be also should be also used step by step to build the geomechanical model, as we have seen here, from data audit to making the stress orientation. The geomechanical model is also later on used for hydraulic fracturing, sand production, compaction, and depletion, as we have mentioned before. Just to notice for non-geomechanics engineers that geomechanics is crucial for both conventional and unconventional reservoirs. So now we have talked about why we use it, where we use it, and how to use it. But before starting talking about the applications, let's talk about what is mechanical earth model or what is geomechanical model. It is a representation of the elastical and mechanical earth parameters for the rock, just to not make confusion between static dynamic models and geomechanical models. For the static models, we can model only the reservoir section or the for unconventional reservoir the source rock section. However, for the geomechanical model, it is an entire representation of the all sections of the logged section from the surface to the bottom. So we have the log from surface to the bottom for mechanical properties and mechanical stratigraphy to get a comprehensive earth stress model from principal stresses to stress orientation, which is used to all applications in the oil field later on. So this workshop is not just an introduction of the geomechanical data and modeling application used in the petroleum industry. Many of the topic here are application listed below require an input for geomechanical model component listed before. So the requiring time throughout drilling and completion operations is the most important thing, which is the elastic stress concentration around the wellbore. So we will go through the first application of the mechanical or mechanical earth model of the geomechanical applications. The first thing is start about mechanical wellbore stability, which is a big issue in drilling and production operations. So the wellbore stability studies typically address the deformation of the intact rock, first followed by the destabilization of the pre-existing plan of weakness, which can cause big issues in the operations and also in the production later on. So the practical definition of a safe window or practical window is the window that is drilled and cased in the reservoir without incident or cost overruns. So to start talking about the wellbore stability issues, so just to mention that we have two issues of wellbore stability. Well, the first one is caused, we call it mechanical failure of the rock due to the drilling and geostresses or due to stress load from the seismicity around the wellbore. The second one is a chemical reaction of the rock with drilling fluids. Sometimes we can get the both, means both occur, but the chemical stability instability, is the domain of geochemists and drilling fluid specialists, so it is not addressed here. We will just focus on the geomechanical issues of the wellbore stability. So just to know that this is a typical safe window chart. So the best well is the well drilled between the breakout limit and the minimal horizontal stress mean within the stable window. So the previous diagram that we have seen here, this one in the right side, now is limited to specific depth, mean in a well corresponding to a specific set of rock mechanical properties and earth stresses. So our task in as geomechanics team is to estimate the stress and the strength variation along a proposed well path, so that we can get safe and stable well pressure window. So here we'll just get some hypothetical wells in a naturally fractured formations. We can imagine that we have three wells drilled in naturally fractured sets: the well one, two, and three. In some intervals of these wells, there is no stable window and rock failure in an unavoidable uh, area. So to manage the well bore stability, it is achieved by managing the delta P, means that the pressure of the well minus the pressure of the formation or the pore pressure. So the key important thing that manage or that interact in the well bore stability is the elastic hoop stress, which is the stress around the well bore, which is calculated as a function of the azimuth around the well bore, given the magnitude of the pore pressure and the two horizontal stresses. So the following analysis illustrates how the well pressure is used to manage well bore stability and also the surface that can fail hoop in the hoop stress. Here we go. So this figure, we have here one figure show an example of the well one. This well drilled just far from the fractures interact with without there is no interaction between fractures. So this well, the well one, where delta P is an optimal delta P. So at the left of the slide, we have a cross section of the well with the two minimum and maximum horizontal stress, and also the sigma theta, which is the hoop stress. And at the right in the variation is the variation of the hoop stress. This variation of the hoop stress in functions of the azimuths from SH max, and we have here the limit of the compressive strength and the tensile strength. So the amplitude of the stress variation is governed by the difference between SH max and SH mean. If the horizontal stress were equal, so means that the hoop stress would be the same at all the azimuths and plot as the horizontal line. So the effect of changing the well pressure is to shift the hoop stress curve up or down by amount of delta P, as we have mentioned before. So the hoop stress does not intersect the stress curve anywhere on the well bore surface. So in this context of the well bore pressure window, this is stable med pressure that plots in the green region. So this one, this well, the well one, it is well drilled in a safe, stable window. This one, this green one. Okay, so now the figure shows an example of also the well one, but where the well bore pressure is too high. So well bore pressure means that the column of our well bore is too high, causing a hydraulic fractures to initiate at the azimuth of SH max. So in the same azimuth of SH max. So the only difference between this figure and the previous one, this one and this one, is that the well pressure was increased. So it means not the reservoir pressure or the pressure inside the reservoir has changed, but it is the well pressure. So here it is problem of the production engineers. So maybe not estimate well the drawdown or the estimate the pore pressure. So here we have increasing the well pressure, so caused this hoop stress increasing in the SH max azimuth. So just to notice that the hoop stress now equal to the tensile strength. Here we have, so our hoop stress touch the tensile strength limit. So if either theta 0 or 180 degrees. So if the well pressure were to be reduced, so the hoop stress would increase by the same amount at all the azimuth. So here, another example of the same well. So this figure illustrates when the well pressure in the well one is too low. So here, here The problem is inside the reservoir. So the hub stress equals the raw compressive strength. So touch this upper limit. So at the azimuth of SH mean, it will cause what is called in the oil industry known by the breakout. Though this corresponds to breakout limit at the low pressure side of stable window. This limit. So here we are in the breakout limits here because the reservoir pressure is too low. So okay, what we have also, so before, so this is the well 2 and well 3. So we will start in talking about the well that intersect the fractures. So well 2 and well 3 show, we will see how the natural fractures can affect the maximum well pressure and also influence the geomechanical behavior of the reservoir. So the well 2 intersect a natural fracture, this red one, lined with the maximum horizontal stress as such max. So the normal stress acting on this fracture is also equal to the magnitude to the least minimum horizontal stress SH mean. So if the well pressure is greater than the SH mean, means that the pressure of the well will be bigger than SH mean, and the fracture delays, and the well starts to lose fluid. And the third well, which is well 3, increase at intersects the three fracture sets. So we have three fracture sets, one aligned with SH mean, one aligned with SH, the red one is aligned with maximum horizontal stress, the green one is aligned with minimum horizontal stress, and also the yellow one, which is in 45 degrees from the both stresses. So the fractures will be with the fractures aligned with SH mean will still open because the normal stress on the yellow and green fractures is much bigger than the minimum horizontal stress. So all this kind of sets is based on the horizontal stress azimuth and also the hub stress concentration around the wellbore. So here we can go through explanations. This is most important fracture set, which is the yellow one. So in these three figures, we have an example of the fracture normal stress as function of the angle. So from the direction of maximum horizontal stress, theta equal 0 to normal stress in is, which is the minimum horizontal stress at theta equal to 90 degrees. So it is the maximum horizontal stress. So these two color dots, the red one and the yellow one, indicates the normal stress on the fractures. So here we have the normal stress on the fracture and the fractures. In addition, we have our formation breakdown pressure. So the opening pressures of the natural fractures can limit the maximum med pressure used to drill this well. So therefore, the magnitude of the minimum horizontal stress is often used as also conservative upper the bound pressure for the stable mid-weight window. So this window. So okay. So now we start to talk about the stability of the deviated and also the horizontal well. So as you know, we are in the 2024. Few wells are drilled today are vertical. We have the unconventional for shale gas and also the offshore fields, which are developed from fixed or the floating drilling platform using multiple deviated and extended each wells to access the reservoirs. So the stability or the arbitrary well trajectory must be modeled numerically, and which is very critical when we are in the offshore or when we are in the unconventional reservoir, which are known to get overpressured, so high pressure, pore pressure of the reservoirs, which can occur a lot of issues in the wellbore stability. So to illustrate and to consider the relative stability of the wells aligned with the three principal stresses. So we have the normal faulting stress regime, and where maximum horizontal stress is slightly less than the overburden stress, as we see in this figure. So we have a three set of wells, three set of the hub stress, where the intermediate, most, and the least stable window. So, just to get some information, so the geomechanics team normally gets involved once the exploration department or the exploration asset has identified the drilling prospect or the drilling area, so open budget and approval. So the exploration asset supplies the subsurface department with a subsurface target, so they give them subsurface target, and also the subsurface department must then prepare a detailed drilling program and cost estimating for testing the rocks at the largest locations. So the geomechanics input is necessary to determine the surface locations, the blowout prevention rating, the casing setting, drill bit selection, and also the most important thing in drilling, which is the wellbore stability forecast, and also suggesting the casing points for the deep water example here, and also for the perforation, which is also important. So the wellbore stability forecast has three part important things. So as we have talked before in the mechanical earth modeling, so the most important thing, which is the mechanical stratigraphy. So we have to start talking about the stratigraphy, or known as the lithology, the vertical variation of the lithology. So the wellbore stability is related directly to the lithology, and also to the which are related to the elastic parameters. So the elastic parameters of the shale are not the same as the sand, and vice versa. So we have to get the mechanical stratigraphy for each well, and also the wellbore pressure window. So this is a list of potential drilling hazard and risk recommendation for remedial action, for example. So here we have a schematic of a wellbore stability forecast. So we have to select the drilling fluids to be aligned with the stable window, so they don't react chemically with the stratigraphic sections. And the wellbore stability forecast also predict either breakout or fluid losses when drilling with pressure outside of the stable window, the stable window. So knowing the drilling hazard and potential risk are identified along with remedial and recommendation plans if some problems occur. So the vertical red line represents the well pressure corresponding to a specific drilling fluid density, and the blue line is the recommended pressure midweight to drill the section of the hole. So here we are in stable window. If we get down, we have to provide recommended or remedial actions before starting drilling. And also, if we are facing some problems here, for example, we are in this area, also we have to prepare remedial actions. All these things should be known before drilling, and it cannot be known without getting a comprehensive geomechanical model and knowing all the elastic parameters, the stress limit, the stress, and also the shear failure criterion that will be discussed later. So we have to know all these kind of parameters before drilling our wellbore. Sorry. Here, just before continue the work, just to test your knowledge. So just knowledge check. So if to see if you are following us or no, or you are sleeping. So what are the primary types of mechanical instability? So just give us answers in the box. I don't know if we can provide the microphone, or we can get answers, or going directly. I don't know what the host thinking about this. I can give you 30 seconds, so just try to be honest and write the answer down on your paper, and after that I can provide the right answers. So here we go. I can set my chrono to give you 30 seconds to think about these questions. So repeat again, what are the primary types of mechanical instability? Are they the deformation of the intact rock, stabilization of the planes of weaknesses, stabilizations of the pre-existing planes of weakness, deformation of overburden, or the stabilization of the overburden? So still 10 seconds to write down your answers, and after that I will provide the right answers. So time finished. So I think that it can provide. So as you see here, the primary types of mechanical instability which are discussed before, are the formation of the intact rock and the destabilization of the pre-existing plane of weakness. Now I think that we have covered most important topics, things regarding the topic of the wellbore stability. If you need big informations and the details should be discussed later on separated workshop or separated course with the Petroleum Engineering Association. So this is should be individual workshop or detailed one with a lot of with the not only one day or one workshop. Okay, so now we will talk about the second application, which is most important in development and also production and also in the depleted fields, which is the sanding production or the sanding analysis or solid production. So, design two main geomechanics application relate to reservoir completion. So the sanding refers to the unwanted production, means that this is not the desired production from reservoirs. So, for example, if you are produce from a sand body, and you start receiving in your wellbore column some solid that you cannot identify them, so you have to go back and see your UCS or your unconfined compressive strength regarding porosity and to see if you are in a weak reservoir, so you are producing under UCS, means that you will expect to get sand production. So the sanding, as I have told, refers to the unwanted production or solid along with the hydrocarbons. So this solid production is challenged in a high porosity or low comprehensive strength reservoirs, mean the sand reservoirs, which is generally restricted to the near wellbore region, but sometimes it can affect the entire reservoirs in the depleted in the means that the very high depleted reservoirs we can get the sand production from the entire reservoirs. So this is excess of solid cause the erosion of the surface equipment and also the failure of the downhole completions. So sometimes you can also go through replacing all your completion due to this sand production. In several cases, the erosion leads to the collapse of the well or solid filling the well for the 1,000 feet or more, both leading to a significant loss of production initially. So this solid production may not be an issue, but also may become a problem later in the life of the field, like I have said in the depletion phases, when you will get water breakthrough occurs or when the reservoir depletion reached a critical state, means that you are in the merely in the end of the life of your field. So method for dealing with this solid production are declassified as the exclusion methods or the predicted method. So the most common method is the gravel packing or design prevent sand from entering the wellbore. But the prediction method or the predicted method is to estimate when the sand production will occur. So you will manage your drawdown within your wellbore and your reservoir. So we will produce safely. You will produce your reservoir with a safe amount, so to avoid this sand production and to manage the life cycle of your reservoir. So here we have a typical cross-section of typical performation in a sandstone and the schematic cross-section through the sand reservoir. So the feature are a zone yield rock near casing. So another zone of crushed rock adjacent this yield zone crushed rock adjacent to our wall. So in the perforation tunnel and the pillows debris at the bottom of the tunnel. So this solid production can only occur if the rock around this tunnel has failed and the rock fragments are transported. These fragments are transported to the perforation. So here we can talk about weak reservoir. So this weak reservoir, so this yield zone, so means that the reservoir start to start being depleted and we are under UCS estimated UCS. So all the solid in the reservoir can be transported from the annular zone crushed rock to this perforation and starting getting solid production. So the salt production is a two-stage process. So the first, the rock must fail, and then failed material must be transported from this tunnel perforation. And also, the failure is defined as breaking cement bond between the grains and both transport solid in the wellbore column. So here we can start talking about two typically type of reservoirs that we can predict sand, and also we can another one that we cannot predict sand. So the first task as a geomechanics engineer is to determine the relative strength among the reservoir. Means that the response from the reservoir to the stress load. Means the reservoir data to be completed. So here in this figure is a schematic of case perforated completion in a low strength reservoir showing two beds, the bed A and bed B. So the A is a weak and cemented sand, means that we are in has UCS inferior than 10 megapascal. So we have no perforation tunnel there. So under in situ stress conditions, and it is not strong enough to support perforation, so it is not perforated. And the second one, which is a B, represent weakly cemented sandstone that is strong enough to support the tunnel. So here we can prevent the sand prediction. However, here we cannot predict, so it is not under control. So what we can see if all reservoirs interval as are as weak as the first one, this one, so the decision would be to complete the zone using a sand exclusion method, such as gravel packer or fractured pack. So this will be discussed later. But if we have a strong or not weak formation, so the rock, if the strong and weak rocks are interbedded, so selective perforation of the stronger interval can be appropriate strategy, like the bed D. So when the rocks are of uniform and sufficient strength of the reservoir, stress management strategy should be used to avoid all the fouling of the rock. That is, so the limit of the drawdown pressure to prevent the sanding. So here it is the schematic of stress analysis of a horizontal perforation. So this following analysis illustrate the basic mechanism of the sanding phenomenon governing the initiation of the solid production in a reservoir strong enough to support the perforation tunnels. So this is our reservoirs that can benefit most from solid production risk analysis, thereby avoiding unnecessary gravel packing. So because of the economic impact of the incorrect completion decision, so the rigorous numerical analysis is to estimate the drawdown differential drawdown pressure. So the objective is predicting the solid production to estimate the maximum drawdown, or how much the wellbore pressure can reduce delta P, the drawdown, so without collapsing the perforation and without getting the shell failure criterion. If you see here, for example, here you are in your initial static stress, but after starting the production, you have your flowing max safe. This is the drawdown limit. So if you exceed this shear failure criterion, you will expect to get all the solid production from your reservoir. So it is very crucial to know the applied principal stress in your field. So you have to know the local stress, the regional stress, and also if you are in seismic area, you have to know the far field stress, how the far field stress influence your area. So all these kind of parameters are crucial in development, especially if you are facing unconventional reservoir production, which is very critical point, because you will produce a lot and you will inject a lot. So the shear failure criterion here is a very important thing to be taken into consideration within unconventional field development, because wrong estimation of the delta drawdown can cause a lot of issues, and you can lose all your project by only wellbore stability analysis issue. Because you know that this drawdown cause a reduction or of the sigma of the initial initial stress state. Sorry. So here we have typical example of perforation stability analysis with the initial drawdown and the final drawdown. So often the solid production only develops after reservoir has been on production for a period of time. Means that production reduces the magnitude of the reservoir pressure and also the minimum horizontal stress. So the perforation stability analysis is shown. So here's the schematically in this limit in this figure. So the green shaded region represent the predicted maximum safe drawdown for solid production after being out of this limit. So you can expect to get solid production. So this is the initial reservoir pressure. Here we have the initial drawdown and also the final drawdown. If you are here in the reservoir, so it means you are in a safe predicted solid free production. You cannot expect to get production. But if you don't manage your drawdown correctly, or you will be here in this zone, so you will expect to get a lot of problems in reservoirs, or the productions, the solid, the solid in reservoir can be start to debit, and you will get a lot of problems in your completion, and you have to close your well bore and repeat another completions. Also here we can make some knowledge check. So the question is to see if you have follow the sending production. So what is the most common exclusion method, not the predicting method, the exclusion method designed to prevent sand from entering the wellbore? Is it sand packing, the gravel packing, hydraulic fracturing, or the perforating? So again, I will give you 30 seconds to answer. Try to be honest and to give the answer. So write down your answers. After 3 seconds, I will give you the right answer. Just focus. I know that we have talked a lot about sandpacking, hydraulic fracturing, perforating, but focus. So the answer, don't be confused. So the answer is clear. Just try to focus. Still 9 seconds to get you to give you the answers. I think that everybody write down the answer. So here we go. I think that everybody know the answer, which is the sand packing. So to exclude sand production from your reservoirs, if you have not made or prepared geomechanical analysis in the first stage or in the first stage of your field development. So here you should use an excluded method. So by using the sandpacking to avoid and try to remedial your reservoir production and not lose a lot of production and minimize the cost. Thanks that we can go through the third application, which is the well-known hydraulic fracturing. So in this section, we will discuss the application of geomechanics relating to hydraulic fracturing for both conventional and also unconventional reservoir, starting with fracturing a stratified reservoir from the vertical wellbore. So, what is the hydraulic fracturing? I think that everyone in the reservoir or production of petroleum engineers, even the GNG, know that hydraulic fracturing is a method for obtaining economic production from the low permeability reservoirs, such as the tight sand or also the shale gas reservoirs, and to enhance recovery in aging oil fields. So, unlike the solid production, these reservoirs have low porosity. So, not like the high porosity reservoirs when we can expect to get sand production. These reservoirs are now to be a low permeability reservoirs with high comprehensive strengths because they contain a lot of fluids, a lot of hydrocarbon that has not been drained to wellbore. So hydraulic fractures are not restricted to near wellbore region, but often extend hundreds of meters vertically and also horizontally away from the wellbore in the case of the unconventional reservoir development. So the goal of the hydraulic fracturing is to maximize the area of contact between the fracture, the area of contact between the fracture and the reservoir to achieve the desired economic production. Here in this figure, we can see borehole stress around the concentration governing the breakdown pressure and propagation direction of the hydraulic fractures initiate from an open hole completion. If you have seen here a lot of problem, we are still discussing pore pressure, geomechanics are also the key parameter in a lot of operations in the reservoir protection or petroleum engineering. So the process of hydraulic fracturing, I think it is one now is to increase the pressure in an isolated section, so to isolate with a double packer, and also to try to get higher than the breakdown pressure of the desired section. After that, to initiate and induce the fracture propagate within the maximum horizontal stress direction to avoid the closing of this fracture later on, and also to optimize our production. So in an ideal homogeneous isotropic rock, so the induced fracture will propagate vertically oriented with the maximum horizontal stress, and also which is perpendicular to the minimum horizontal stress. So here in the left side of our figures, sorry if you, I don't know if you see my mouse. So the diagram of open hole completion here illustrate the magnitudes, and orientation of the hoop stress concentration at the fracture initiation pressure. So if you see here, so we have the magnitude of the hoop stress and the orientation of our hoop stress on the induced fracture propagate as the mode one extension fracture in a plane perpendicular to this minimum horizontal stress. So we have to be parallel with maximum horizontal stress to let how these azimuths and these magnitudes help the fracture to be not closed within borehole within the reservoirs. I think that that's all for the mechanism of hydraulic fracturings. So just to know that high breakdown pressure, high breakdown, if we have high breakdown pressures and poor proppant transport results, when a complex fractures transport result when complex fracture from perforating reservoirs. So here just to give some informations how we can use the geomechanical information to go through hydraulic fractures. Here we have an example of reservoir with the two bodies, shelly bodies. So, and here the profile of minimum horizontal stress and the elastic modulus. This is the fracture width. So the elastic parameters, which are the Young modulus and Poisson's ratio, are used to know if we have barriers or no, and also the stress profiles to know the initial breakdown pressure to prepare our fracture design and the proper propellant, the necessary propellant, and also the power horse in the surface to get into these reservoirs. So if we have no shelly barrier here, of where the minimum horizontal stress or the closure pressure or also the breakdown are very high. So the fracture hydraulic fracturing will be very difficult, and we cannot. In sometimes, I remember in some fields, the reservoir pressure is around 9,000 psi, or in this some cases, one 10,000 psi. So with the power horse of 4,000 psi, we couldn't achieve the hydraulic fracturing propagation. So we have to get a comprehensive and also calibrated geomechanical model to know the behavior of the reservoirs within the fractural hydraulic fracturings. So also to notice that the stress contrast need to be sufficient high, typically around 250 psi contrast. This contrast to get a good confining of the proper fractures. So we have to get this contrast of around 500 psi to get a confining probation, not go bypass the reservoir. So when the contrast is very high, the fracture is contained, and when the stress contrast is too low, so we have the high growth we occur, western flutes and propellant or unprojective zone. So if the contrast is too low, so we can bypass the reservoir, and if your reservoir are in water zone here, you can get water production, and you will damage your production. Okay, I think that's all for these completions. So As you know, nowadays aggressive exploitation of the shale gas reservoirs in North America has highlighted the importance of the elastic anisotropy on the hydraulic fracturing simulation. So before we tend to use only isotropic estimation. So we thought that all reservoirs are isotropic. So we design our hydraulic fracturing to be isotropic. But a lot of information gathered from the unconventional reservoir exploitation in the North America, in Argentina and China, has shaded the light on the importance of using TIV anisotropy model. So the most of the shales, are characterized by laminated shale. So this laminated shale tend to be transverse isotropic elasticity, means a TIV model with an axis of rotational symmetry perpendicular with an axis of rotational symmetry perpendicular to the rating. This is an example of TIV or shale reservoirs. This is laminated shale reservoirs that tend to get TIV symmetry. So here, example of young modulus and process ratio response within elastic modulus for a TIV shale. So for a TIV material, as you know, the young modulus and in X direction and Y direction are different, and also for the Poisson's ratio or the physical and elastical parameters should be different in different axes. Okay, so why anisotropy is important in shale gas reservoir? So as you see here in this comparison of the minimum horizontal profile for well drilled in the Baxter shale, if you see here, we have if you estimate the minimum horizontal stress in the red line with isotropic approach, and see here if you estimate it with anisotropic rock, and also you see here the pore pressure and the overbend pressure. So if you see here, if we go through isotropic approach, you see that the stress is very low than the stress estimated with anisotropic rock. So if you perform a hydraulic fracturing, so you will estimate your stress to be just to avoid to bypass this isotropic minimum horizontal stress, but you will get surprised because you are facing an unconventional formation with anisotropic behavior. So you have greater stress contrast, and also all the behavior of the fracturing is not the same. If you see here, we have contrast between this zone and this zone also here, so not the same behavior. So in conventional reservoir, be careful using isotropic approach, which is very dangerous one, because in unconventional reservoirs the anisotropy is very important, and in the anisotropy approach you will use the stress, the far field stress influence, and also the anisotropy of stress. This one, the anisotropy of stress load, and also the anisotropy, the intrinsic anisotropy due to heterogeneity of the reservoirs. Okay, another knowledge check. So the primary factor governing fracture containment is the stress contrast between the reservoir and the bounding beds, the reservoir and the casing and the cement, or the reservoir and the bounding beds. Repeat again. So the primary factor governing the fracture content is the stress contrast between the reservoir and the bounding beds, the reservoir and casing, the casing and cement, or the reservoir and the bounding beds. Also, I will give you 30 seconds to write down your answers and try to be honest. And after 30 seconds, I will give you the right answer. If you have followed us, I think that I'm not doing very quickly. I'm trying to explain with example. So the primary factor governing the fracture contained is the stress contrast between the reservoir and bonding beds, the reservoir and casing and cement, or the reservoir and the bounding beds. Still 4 seconds to give you the answer. I think that everybody can answer. So the answer is the primary factor governing fracture containment is stress contrast between the reservoir and the bounding beds. This one. This one. Okay. Okay. So now we will go through, I think, the fracturing of horizontal wells means that the methodology to fractures the unconventional reservoirs. The set or the principle of fracturing horizontally is not as the vertically, how to say, vertical hydraulic fracturing. So the K geomechanics information needed to support the fracture stimulation of horizontal wells as the same as the conventional. So we have to get a vertical overburden profile, maximum horizontal stress, the minimum horizontal stress, estimation of our pressure, and also the most important thing is the azimuth of maximum horizontal stress, which is crucial because you will drill in a horizontal way. So in the shale gas production, to achieve hydraulic fracturing of these soils, so the reservoir optimizations requires knowledge of all these stress profiles, and also the knowledge of the stress orientation of the wells what are drilled and how to be fractured. So this call for careful planning, data acquisition, and fracture design to be careful for horizontal hydraulic fracturing. So in effective reservoir stimulation is achieved when the horizontal wells are drilled in the in the direction of this in the direction of the principal horizontal stress SH mean and SH max. So if you see here, we are not in SH mean and not in SH max. So this is the optimum direction. So if you drilled here, you can fractured parallel to SH sorry, if we drill our well parallel to SH means that we have to fractured against SH max, which is very dangerous in our well bore stability, and the opposite side we will not get opened fractures. So we have to be careful to get an optimum direction if the lies geometry of hydraulic fractures in multi-stage. So this is the optimal horizontal well drilling and also for fracturing. So if you fracture your well within the direction, so the fracture will still open because you are parallel to maximum horizontal stress, and also the minimum horizontal stress is less than maximum horizontal stress. But if you are in the opposite direction, the maximum horizontal stress will close the fracture and you will lose the production. So here we have example of stress concentration on a horizontal A well and the vertical well B perforated. So the most of horizontal wells are stimulated from cased hole completion. You know that. So this completion option provides greater control. So if you stimulate in a cased hole or in an open hole, it is not the same as you know. So this completion provides greater control of where fluids are injected. So to some extent, fracture geometry by selecting the location and orientation of your selected perforation. So here, this figure show the idealized stress around the perforation slot from horizontal well drilled at the azimuth of minimum horizontal minimum horizontal stress, and as the red line indicates fracture, the red line indicate the fracture initiated from horizontal and vertical perforation. That may be coplanar if the perforation are coplanar. So if the well is drilled on the direction of the maximum horizontal stress, the perforating only the vertical. So we have to perforate only the vertical plane with promote fracture that propagate along this axis. So the completion with this idealized description fracture stimulate may be caused by natural fractures or also perturb the in situ stress field affecting fracture propagation path and also the reservoir productivity. So while the influence of the natural fracture can be recognized by microseismic monitoring, so we have to monitor your fracturing if you are dealing with unconventional field development. You have to provide microseismic set to monitor your hydraulic fracturing. So the lateral variability is determined by logging horizontal wells to avoid the induced seismicity, and to see also how your fracture is propagating within your reservoir. I think here, just to come back for gravel pack vs frac pack compression. So as you know, the deep water reservoirs typically are poorly consolidated and require solid exclusion using this gravel packing or fracture packing. So this is a schematic of the exclusion method to provide for solid protection. And also I have let this at the end because at the first time we didn't talk about fracturing. So this is one of the excluded solution are fracturing for sand control. I think that also we arrived at a knowledge check. So the reservoir optimization decision required the knowledge of the stress profile and stress direction. So the horizontal well is drilled before, during, or after. Repeat again. So reservoir optimization decision required knowledge of the stress profile and stress direction of the horizontal well is drilled before, during, and after. Okay, you have 30 seconds to answer this question. Okay, so we have to know the stress profile and stress direction within the horizontal well is drilled before, during, or after. Okay, 30 seconds to give you the and write down your answers. After 30 seconds, I will give you the right answer. So I think still 10 seconds. Of course, we have to get knowledge of stress profiles and stress orientation before making the horizontal well is drilled. So now I think that I will give you just an example and why geomechanics is so important in oil and gas field. So here, if you see with me, so this is practical cases. It is case study. This is a published case study. If you follow, this is one of my recent published videos on my YouTube channel. So here, if you see here with me, this is reflectivity maps of one of the reservoirs in the North Sea. This is four wells drilled. The A, B, this one, the A, B, C, D. This is within the same reservoirs. So a petroleum company thinks that the gas. So they drilled these wells, and they thought that the gas has leaked from the reservoir. So they found from some wells they found gas, and from the others they didn't find gas. So they thought that the gas has leaked off from this reservoir. So to understand that concept, they bring this reflectivity map of the top of Brent formation. So the blue is the blue is low reflectivity, and the red one is high reflectivity map. So to see how the gas has leaked off. So the gas had leaked off, and in fact there is a bit of gas cloud above this reservoir. So above this top of this reservoir, they find gas, but in this reservoir, the same reservoir characteristics. Some wells contain gas and others does not contain gas. So the company has actually drawn this dotted line to indicate where the gas cloud was and where they think the gas has leaked off. So the question is, why did the gas leaked out? And so what we will see here, and we will show you when we get to that details how we did this calculation. So if you see here, if you can see here me, this is they bring this stress orientation, maximum horizontal stress orientation of these wells. If you can see here, this is the orientation, stress orientation of the well A, B, C, D, E. This is the stress orientation. So if you see here, you can see the stress orientation of the well A is in this direction, the stress B that direction, and after here in the well E, you see that we have like this east-west orientation. So here we go. So the gas leaked out because of compressive stress that reactivate this fault. We have this fault. So the reactivation, the stress that has reactivated this fault made a stress reorientation. So this stress reorientation has been induced more or less in the last 15,000 years. So if you had drilled your wells here 15,000 years before, you can find gas, but now you cannot find because this fault has been reactivated 15 years ago. Here are the proof of the reactivation. We have stress reorientation, present day stress reorientation due to fault reactivation. So this fault has been reactivated, and the gas has been leaked from this reservoir to the top, the above formation. But in this area, the gas has not been leaked off. So if you see here, not the same stress characteristics and not the same stress orientation. So this fault has been reactivated in 15 years before. So the hydrocarbon where they have now leaked out because of this fault reactivation and the result of natural geological process. So we can start talking about a compressive stress reactivation. So this fault reactivation has caused this leak off, and if you drilled your well 15,000 years before, you can find hydrocarbons. So here you can see the importance of making geomechanical and stress analysis before going through your field development. So I think that this is very important example to know the importance of geomechanical in practical and case study view. So here we arrived at I think that the coupled geomechanical model. So we will not go through this detail, but you have to know that if you are facing reservoir or simulation modeling, you can make also a geomechanical model for your simulator. So based on the dynamic model, you can use also this the geomechanical simulator. So you will make input of your geomechanical model to the reservoir simulation to get a geomechanic simulator. So you will increase your reservoir estimation and also your reservoir modeling by adding the time dimension making 3D, or also you can make a 4D geomechanical model. Also, this can be discussed later on separated topics. We here we have a hypothetical shale gas reservoir with three sets of natural fracture. We will come back to practical cases. So here in these figures, we show a map view of reservoir containing three fractures as the first one when we talk about where's that intersect fractures. Here we have a reservoir containing three fracture sets in relation to the far field horizontal stress as maximum horizontal and minimum horizontal stress. So here we have a case that the far field stress act on our local stress, influence the local stress. So we can assume that the state of stress is uniform, so throughout the reservoir, and the fracture comprehensibility is the same for all the stress. So we imagine that it is the same for all. And to the right, we have the more circle column representation of the initial stress state of the fracture set number 2. So the shear effective normal stress here shown by the dotted gray line. So when reservoir pressure increase, the effective normal stress decrease, and the more circle shifted to the left of our shifted to the left of our reservoir. If you see here, so when the displacement happens fast enough, microseismic events can be occur. So we have here we attend the shear failure criterion. So this is what often happens when naturally fractured shale reservoir are stimulated by hydraulic fractures. So be careful in conventional reservoirs. In a lot of cases happen. Also, when you are dealing with carbon storage projects, you have to be careful. Also, when you are injecting in a reservoir with high pore pressure, you can expect to get these things. And also, if you are depleting a reservoir with a high drawdown difference, you can expect to get this. So this is what often happen when in unconventional reservoir. So this dotted line, this green dotted line, represent the initial state of stress of the fracture set 2, and how this stress has been changed after production of this unconventional reservoir after hydraulic fracturing. So here you see the fracture permeability variation with the normal stress. So if, as we know, the anisotropic stress impact the permeability of anisotropic reservoir. So this uniform change in the reservoir pressure change also the permeability of all this set of fractures, but the different amount of each set depending upon the initial fracture, depending on the initial stress state. So this change in reservoir also, as I have mentioned, that it will impact the permeability of our reservoir. So here we see the impact of the effective normal stress on the fracture permeability and the change in reservoir pressure. So if we consider how a change in reservoir pressure affect this permeability, so also we assume that the fracture permeability obeys in parallel plate from rate permeability. So since this fracture aperture is a function of this effective normal stress, so the change will or the change of effective normal stress will get a directly impact on the fractured permeability. So here we see clearly that fracture permeability varies dependently with effective normal stress, and also we see that the fracture orientation relative to our horizontal stress. I think that we arrive at the end of our workshop. Just to mention that unfortunately, geomechanics is not involved in oil field operations until there is a problem or issue or an incident. So the challenge is to figure what happened and to recommend remedial actions after all happens. So they call for geomechanics engineer or for subsurface to remedy this action. So the sequential workflow for diagnosing the root cause of geomechanics problem is to review the engineering basis of design, review operational activities leading up to events, determine the deformation was caused by unexpected stress or rock swells, geological structure, or failure to follow the design, and also to recommend the change in design or operation practice or both. But ideally, a mechanical earth model or geomechanical model is developed early in the life of your field, and it is updated as new information become available. It is not static model. It is updated by each information you get. You have to update your geomechanical model, and this is proactive approach enable the diagnosis and recommendations to be completed relatively quickly and improves effectiveness of your field development and your reservoir management. Thank you for following us, and see you in separated topics of all this what we have discussed here.